Okay. So, we will start from what we were discussing in the last class. I will go back a little bit to this, beyond this point, yes. So, when you have this is your PB cell with potassium phosphorus and boron doping, right, phosphorus and boron doping, etc., and then the metal. So, basically voltage is generated here as soon as the light falls onto it, that we have talked about. And if I do not put a load and keep it off, switch off, then that potential we call it open circuit potential. That will be maximum potential, because when it gets shorted or connected, let us say, through the load itself, the current will pass through the whole thing, some EMF is lost in driving through the current through the cell itself. So, therefore, open circuit potential is the maximum potential, and current would depend upon the load, and when you short circuit it, no load here, that is the current is maximum, because there is no load, right. It is something similar to, you would have remembered from battery cell. So, open circuit one is, because potential, when you measure open circuit potential, potentiometers or voltmeters, their resistance is very high, practically no current passes. So, therefore, it gives you what is the available total voltage, but the moment you short it or connect it through a load or otherwise, the current is, there will be some EMF will be lost in driving the current through this. So, that is what it is. So, this is why, this is what we looked into in the last class. I do not think I am going to look it right now, and this open circuit potential, the expression for the same is something like this. If this is the band gap, this is the band gap, this is the band gap energy of the band gap energy. So, because it would depend upon band gap energy, right, as we have discussed earlier, and Q is the charge. So, potential is energy per unit, is the work required to move the charge in an electric field by unit distance, if you remember that. So, basically energy per unit charge is the potential. So, this is one part. Second part is related to basically the temperature and the light that is falling in, right. So, this is actually number of electrons, is the number of electrons, increase in the concentration of electrons induced by light. So, number of electrons that jump or concentration changes, and this is the NC and NV are electron densities of conduction band and valence bond respectively. In fact, this is related to probability. I do not think I am going to go into that, and this is Boltzmann constant in electron volt. Now, you can see that this is actually dimensionless. These are the electron density because of the light. This is also number of electron or electron densities both in the conduction band and valence band. Therefore, root over multiplied by 2. So, root over. So, this is dimensionless anyway. This is in Boltzmann constant in electron volt, right, per Kelvin. So, multiplied by Kelvin temperature, that means this gives you electron volt, which is the measure of energy, and if I divide by the number of charges, then I get volt. So, this is the expression for VOC, open circuit potential. This is temperature in Kelvin and band gap energy, etc., etc. So, one can actually find out the open circuit voltage from the fundamentals, but we do not need really for our purpose, but we must understand this. Now, if you look at the current flux, now current flux is defined as I divided by A, it is I divided by A. I is the current per unit area, because I have a cell area through which current passes. So, this is the current flux, and that must be that due to light, and there is some amount of reverse current generated, right. When it tries to move, there is a kind of reverse current generated, and this is related to the J is the current flux, subscript light is the flux due to impinging light, this is due to light, and V is imposed potentials, subscript 0 denotes reverse saturation current. So, there is a reverse current generated, because as you increase as you increase the voltage, as you increase, it is asymptotically, it tends to, it will not increase proportionally. So, there is a reduction. So, this reduction reverse, this is reverse saturation current as it is called, and Q is the charge of an electron. Of course, this is the charge of an, Q is the charge of an electron. So, as the light passes, the current flux would be reducing. J0 stands for, this is the saturation current. So, as you increase the current, there will be a reduction, and this is that, J0 is reverse saturation current. So, this is basically there will be a reduction, and that gives you the reduction, because whatever, everything is not converted. So, current that you get is that you get from the light, plus there is some kind of a reverse current, and which reduces down, and that is what it is. So, that is what it is, and it is modeled, as I mentioned earlier, that the light J light would be something like this, and since it is one directional, there is a diode, and there is a parallel resistance and series resistance, that is how it is modeled. So, this system is modeled with photocurrent, a diode, and a shunt, that is parallel resistance as a series resistance, right. And one can write like this: J light, J diode, and J shunt. That is in a macro level expression for it. And this was that reverse saturation current, and this is the current, because this is the current generated series. This is, this is the voltage, because this is the flux multiplied by per unit area. So, everything is per unit area. So, per unit area multiplied by this is the total voltage drop, because this is the total voltage drop in this circuit. This is the light, this is the diode, is the reverse current, reverse saturation current, and there is a series resistance, and the shunt, because this is the total potential along the line, and this is divided by R, that gives you the. So, this is simply from this equivalent circuit one can get this, from this equivalent circuit one can get this. All right. So, what one sees is, when your current is 0, open circuit potential, voltage is maximum, and when it is shorted, the current is maximum, and in between at different loads, this keeps on, this keeps on changing, it reduces. You put some load, it would reduce, this would reduce, and say at this point, this is the current and this is the potential you will get. So, there is a point where it is maximum, power is maximum, power is basically nothing but I into V. So, this point where I into V is maximum, P max, maximum power point, I into V is maximum, and generally operating point could be somewhere away from this, not only as the maximum, right, and obviously slope is V by I, slope is V by I, potential, so V by I is the slope, I is this side, V is this side. So, slope is given by this. So, maximum is this operating point, which is I into V. So, this is maximum I into V, dV di is equals to R, okay, in series at this point. So, that is what it is. So, you can correct them in series and parallel, a number of them, and sum total one can find out. So, there will be, for example, there are several cells. So, these cells are all in series, this is in series, and this set is parallel to this. So, total voltage generated you can actually find out from the sum, right, and total current will be summed through each of the parallel paths, total current will be through each of the paths. So, this is what it is to start with. So, that is what it is. So, cells in series voltage adds up, cells in parallel current will add up. So, this is, as you can say, this is all in series, CD, AB, they are in series. So, voltage, total voltage will be from number of them as you have added, and total current would be sum from all of them. So, this depends upon how what is the layout of your cells in the overall. Now, this ones depends on temperature, this one actually depends on open circuit potential as well as short circuit current. These are all function of temperature, these are all function of temperature, these are all function of temperature, and this is a kind of a coefficient for voltage, and this is a kind of coefficient for current. So, alpha short circuit, beta open circuit, these are coefficients, temperature coefficients, and this is for power, this is for beta OC maximum power and so on, delta for power and so on. So, sorry, this is voltage corresponding to beta MP corresponds to beta corresponds to voltage, temperature coefficient for voltage, alpha for current, alpha MP is for maximum power condition, alpha SC is for short circuit condition, this is for open circuit and this is for again maximum power. And for power similarly one can write temperature coefficient, because these are function of temperature. As you have seen earlier, we said that it was if you recollect, it was K, T, etc., etc. So, it depends upon temperature. The VOC is a function of temperature. So, one of the simplest way of dealing with it is through assuming that basically assuming that say alpha alpha is 1 by I di dt. So, the alpha is a coefficient which is proportional to rate of change of the current with temperature divided by the temperature itself. That means, this will divide normalized with, similarly beta is nothing but 1 by V dV dt, and if I talk of power, then it will be similar. So, if I expand this, say if I expand this part, let us say, let me keep this. So, voltage part first, let me look at it. So, beta is 1 by V I said, and let us say my temperature is with reference temperature is 25. So, this would be voltage corresponding to open circuit voltage corresponds to 25, or let me write it, this is how I write it, minus VOC at V, this is VOC at T minus VOC at, okay, let me clear it up and write it again. Beta can be written as, because we said it is 1 by V dV dt. So, I can write as 1 by V, I will and say I am interested in 25 degree centigrade and some temperature. So, VOC at temperature T minus VOC 25 divided by T minus 25. So, therefore, one can so beta can be related, from this you will get this kind of a linear relationship, because you can write it as beta V T minus 25 is equals to VOC minus VOC 25. So, if you rearrange this, you will get this kind of expression. Therefore, this coefficients allows us to find out the open circuit potential at a given temperature, if I know at some standard temperature already, or if it is standard, because measurements in the lab or the factory would be done in standard condition, measurement in the factory. So, at any other temperature I want to find out, I can find out. At maximum power, there is a similar equation. So, this is defined, one as the open circuit stage, another as the maximum power stage. Similarly, for current, one is drawn, one is written at short circuit, another maximum power. Now, P MP, therefore, one can express in the similar manner, P MP one can express in the similar manner. So, delta MP will be maximum power situation 1 by P MP divided by d MP dt, and P can be written as V MP plus I, power is nothing but I into V. So, I can write it like this, and then so divide this power also is written as V MP by I MP. So, this can be written as two sums of this two, because d partial derivative. So, I MP, so this will be written as I MP if I do it this find out this derivative of this one I MP, or let me write it in a better manner, this d V MP I MP divided by dt will be written as first I MP dV V MP dt plus VMP DIMP dt, chain rule. So, this divided by these two, IMP will cancel. So, I will be left with 1 by VMP DMP B dt, this is what it is, and this is nothing but one of them is beta, another is alpha. So, the temperature coefficient for power is the sum of temperature coefficients for current and voltage. So, this is also another thing known. All right. So, power efficiency therefore more are more important. So, this is just some basic fundamentals, and let us look at this. We define power efficiency in terms of the ratio of maximum power to the incident radiation power, right. Generally varies from 6 to 20%, but it can go up to 40%. So, generally 6 to 20%, 22% for varieties of them, that is there. So, first let us look at the definition. This is the efficiency corresponding to maximum power condition, right, power that you can get, electrical power you can get, divided by incident radiation multiplied by area, because this is in watt per meter square multiplied by meter square area. So, area of the cell and incident radiation on it, and maximum power generated, this is the maximum power efficiency. This is same as in the standard condition. So, if I take a standard condition, I know what is my IST, that is the standard, the incident radiation I am considering, then this is how I define the efficiency, efficiency is defined this way. So, this is the electrical power, this is the actually radiation power that is coming in, radiation that is coming in, solar radiation that is coming in. So, this varies from 6 to 22%, some cases can be 40% or so. Now, this I think we will have a diagram of this kind. This diagram is available in net or books or anywhere. Varieties of, for varieties of types of solar cell, what is the efficiency? So, you can say that maximum somewhere go to 40, and this colors single junction, right, single crystal, concentrated thin film crystal, etc., and the lower ones are the green ones, amorphous stabilized nano, polysilicon and so on, and red ones are somewhere there. So, depending upon the types of cell, this kind of a diagram, but this is available in net. Anywhere books or nets you will get it. So, one can choose, for example, these types of one multi-junction cells, single junctions ones, and crystalline silicon cells, germanium, and this is single junction germanium, and germanium and AS cells. This one gives you high, multi-junction cells, this gives you high. These are the next ones, crystalline silicon gels and thin film technologies of the various kind, they are somewhere there, and emerging PVs somewhere they will be there. So, this is 2015 or 2010, this is the scenario. So, that is how the efficiencies are. So, generally you can, one can look into what is available in the market and choose accordingly. Okay. So, this is one aspect. Then let us look at how should we specify and how do we calculate, let us say if there is efficiencies to be calculated. We have defined the efficiencies now, we have defined the efficiency now, which is the electrical power generated divided by radiation multiplied by the area, solar radiation multiplied by the area, wattage from the solar radiation. So, part of the power incident will be absorbed, whatever comes in onto your panel, let us say horizontal panel for simplicity purpose, part will be absorbed by it, part of the radiation will be absorbed, part and rest of will be, some part will be converted to current and rest will be conducted back to the ambient, because this will get heated up. So, there will be some amount of radiation back. So, if I look at energy balance, right, because a part of it is only coming. So, efficiency is related to that, because finally what is the electrical power I am generating divided by whatever is coming in, but whatever is coming in all will not be converted into electrical power. A part will be absorbed in the system and part will be radiated back to the atmosphere. So, this is the kind of equation which shows the energy balance. This is the incident radiation, this is the area of the cell, alpha is the absorptivity, tau is a term, this is the term, this is what actually net it is coming, and k is a factor for angle, k is a factor for angle. This is the power generated, photovoltaic power generated, and this is what is lost to the ambient. This is the U value of the cell. So, if it gets heated up and cell temperature will become higher, which is actually an unknown for us, and ambient is known to us. So, the heat conduction will take place because this will get heated up from this to back to the ambient. So, this is lost to the thing, and this is the power generated, and this is what is received. So, your efficiency will be this divided by the actually this. Okay, let us see how it is. So, tau is transitivity, alpha is absorptivity, I is the current, and U, as I said, U value, I think we would have discussed sometime, 1 over U is the insulation, area of the cell, and K is what is called an incident angle modifier. So, K is given by a formula like this, K is given by a formula like this, where theta is the incident angle, B is a constant, and C is also another kind of empirical constant, right. For theta greater than 60 degree, K is linearly related to theta, not in this manner. So, there is an empirical constant, this value should be available to us generally, and so this is the, depending upon your angle of incidence at which the radiation is falling, this is, this is basically what we are calling it as a incident angle modifier. So, amount of radiation that will fall in would depend upon the incident angle, because there is both diffuse, direct, everything is involved. So, we are not simply calculating out the beam radiation, but in radiation I am multiplying by a incident angle modifier, otherwise it would have been simply cos I and things like that, but we are multiplying with a modifier. So, this is what it is, and T cell is replaced by nominal cell operating temperature. T cell is the cell temperature which is unknown actually, because how much it will get heated up. So, one way is to nominal cell operating temperature on an average basis measured at IC at 800 square. So, this is this can be, I can replace this by NCOT in standard condition when I is equals to 800. For I equals to, so if in the factory or laboratory, if I have to measure, factory laboratory I measure, then I find out what is the C. So, the T cell, that is called NCOT, and when I is equals to 800. So, that is how, because that would be known to me, that would be known to me. NCOT is a standard condition. So, actual cell condition I might be able to calculate out from this. Let us see if we can do that. So, measured at IC 800 and ambient temperature of 20 degrees centigrade. Now, everything will change as soon as your ambient temp changes and radiation changes. So, I fix a radiation, and under that condition we found out this once, which will be available to us, the manufacturer will give us. So, if I put it here in this one, since IB is nothing but power, and this can be written as power generated. So, if I know efficiency is nu and 800 under standard condition, 800 is a watt per meter square is the radiation intensity multiplied by AC. I can replace this by efficiency multiplied by 800, to arrive at certain things which you should see, right. So, this I can replace, by 800 under standard condition, and then this will be NCOT, then this will become NCOT. So, if I take IC is equals to 800, nu ICAC is equals to the power generated, this is the efficiency, and so I write it like this, right. If I write it like this, replace this by 800, this is by nu ICAC, because this is efficiency multiplied by the input radiation, which is 800 into AC. Then you can see that I can get an expression for NOCT, and this take it ambient as 20. So, at 20, which is the laboratory condition, and this is the nominal operating cell temperature, I can write an expression like this, and you can see that from everywhere these terms will cancel out, right, AC, this terms will, I mean AC will cancel out, not this, these two terms will cancel out. So, U NOC, I can take this common, so let me just redo it again. So, AC will cancel out from all of them, and if I take it out UI on this, so I take 800 nu common, nu into 800 common from this. So, I get k tau alpha minus nu into 800, right, equals to n COT UI, UI NOCT minus 20. So, NOCT 20 divided by 800 is equals to this expression you can get. You can get this expression, right, you can get this expression. Okay. This depends upon angle of incidence, this is the property, this is also the property, absorptivity, transmittivity, etc., efficiency of the system, and U value is known, U value of this cell should be known. So, one can obtain this. Now, supposing instead what I do is I put IC, not this 800, in this condition I put, and replace this by nu into I, nu into basically IC into AC, nu into, because this was for standard condition, this was for standard condition where I have put this as 800. Instead, let me write this as nu into IC into AC. Again, AC will get cancelled, and I will get an expression of this one, and this equals to this, because T cell minus T ambient instead of nominal operating cell temperature minus 20, I will get T cell minus T ambient divided by IC. So, this T cell now can be calculated. You see, if this is known, NOCT is known, nominal operating cell temperature when standard condition of 20 degree ambient, 800 is the incident radiation. Then if I know what is my ambient, what is the IC coming in, T cell I can calculate out, because the actual performance will be at the T cell level, right. So, this is important actually. T cell is equals to T ambient from this expression, from this equating this to T cell will be equals to this multiplied by IC plus T ambient. So, that is what it is, T ambient IC, right. So, also this is equals to T ambient NOCT 20 80, this is known to me, this will be known because this is a laboratory state where I have measured everything, and 20 degree I have kept, 800 is the incident radiation I have. So, this is for the given radiation that I will have in actual condition, and actual efficiency inside that I can find out, or so UI is a U value of the whole thing. So, that is how I can find out, right. So, T cell I can find out provided I know. Also efficiency was this, and P solar is equals to P MP, if you remember, it is a function of temperature, and this was T cell minus T standard condition. For standard condition T cell minus TSC 1 delta MP, because standard condition I know and cell temperature I know. So, P solar will be given by this PMP, and remember this power, this efficiency we have written in terms of PMP divided by IC. So, this if this is standard, if I take ISTC and AC, and this one power I replace by PSTC multiplied by this, basically P solar I can relate like this, because IC standard condition IC set standard condition, this since this is PSTC by ISTC into standard condition, this I can find out, and for solar if I want to find out, I have to multiply it by K into IC, how much is the coming, how much is the incident actually. So, this will be given by this formula. So, P solar, power solar available by will be given by this formula, where this is the intensity of radiation falling in, this is the cell, and delta MP is the temperature coefficient power for power T cell minus STC, and this is the standard condition efficiency which will be known to me. But what won't be known to me is, of course, N in this will be this, I mean otherwise this would not have been known, but these two are equated. So, that is how we can find it out. So, you see, new solar one can find out nu STC minus 1 minus etcetera as I said. So, consider let us say I STC is equals to 1000 watt per meter square, then one can get use this expression to obtain P solar from this particular one like this. So, this is what it is. Now, we can look into the specification, what the specification will get it, and one simple calculation of the efficiency out from this.